recall, in the last few lectures we had discussed a number of things regarding the design or synthesis of finite state machines. We talked about the broad categories of finite state machines, the Mealy machine and the Moore machine, and we showed the different steps that we typically follow in the synthesis or the design of such finite state machines, like the creation of the state table or the state transition diagram, then creation of the so called excitation table, then the transition and output table, and finally, the functions are minimized and the combinational circuit part of the sequential circuits are synthesized. Now, one thing we just mentioned, but did not discuss how to do it. Given the specification of a finite state machine, let us say in the form of a state table, how to minimize it? There may be some states which are redundant, or there may be states which are equivalent. We can possibly merge the two states into a single state, that will make the state table smaller, and in the process the final sequential circuit or FSM will also be more compact. So, the topic of our discussion today is minimization of finite state machines, the first part of it. Now, let us see the basic idea. The basic idea, one thing let me tell you, that the kind of sequential circuits or sequential machines that we are discussing so far, they are the so called synchronous sequential circuits. Synchronous means there is the concept of a clock, the clocks are fed to all the flip flops that are used to implement the state variables, and all state changes occur in synchronism with the clock pulse. So, when the clock pulse comes, only then the states will change, and it is expected that the inputs that are coming from outside, they will also be applied in synchronism with the clock. So, we are continuing with that assumption that our sequential circuits or FSMs are synchronous in nature. Okay. So, here we are talking about the issue of elimination of redundant states. Now, the concept of elimination of redundant state is to identify something called equivalent states. So, the basic concept is we want to identify equivalent states. For example, in a finite state machine we can say, or we can find out that two states, let us say A and B, they are equivalent. So, we can merge them together into a single state, that will make our FSM smaller, and that is expected to lead to a more compact representation. Now, when you talk about equivalence of states, let us try to understand what we exactly mean by that. Two states, we are saying that they are equivalent. Now, you recall in a state transition diagram what we have? In a state transition diagram we have states, there are transitions, and transitions are labeled by some inputs, and they also specify some outputs. There may be some other state which is possibly going to the same state, they may be having some other inputs and some other outputs. Now, we are trying to answer the question, these two states A and B, whether they are equivalent or not, right. So, let us try to just answer this question in a slightly formal way. We talk about something called state equivalence. Here we are saying that two states S I and S j, they are said to be equivalent if and only if for every possible input sequence. For example, this alpha and x, these are some input sequences. What I am saying is that for every possible input sequence, let us call it x, the outputs will be the same and the next states are equivalent. So, what we are saying is that suppose I have a state S I here, I have another state S j here, I am finding, let us say there is a single transition only, let us assume. So, here let us say for the input combination 0 0, the output is coming as 1, here also for the input combination 0 0, the output is coming as 1. So, this is what is mentioned here, for every input sequence x, this 0 0 is our x, the output is the same and let us say the next state is also some S k. So, if the next state is also the same, then we say they are equivalent, but this definition says that the next state may also be equivalent, which means say instead of S k, let us say the first one is going into a state S k 1 and this S j is going to a state S k 2, and we have earlier found out that S k 1 and S k 2 are equivalent. So, even if they are going to two states which are known to be equivalent, then also we can say that S I and S j are equivalent, right. Now, mathematically speaking, if lambda denote the output function. So, that is saying that the output when you are in state S I and input is x, this output must be the same as the output when you are in state S j and the input is x. Here lambda is the output function. So, lambda omega we denote the output function in just using various symbols, and delta is the next state function, which says that the next state when you are in S I, the present state and input x, and the next state when you are in S j and input is x, they are equivalent. You say I have not shown it as equal, they are equivalent. These two states should be equivalent. So, when you have this kind of a condition holding, then we say that S I and S j of the machine are equivalent. Just to try to understand that if there are two states and if I find that all possible inputs that we apply from those two states we are going to the same equivalent state and the outputs that are coming are also the same, what does that mean? It means that we cannot distinguish between these two states, they are basically the same. So, we can merge S I and S j into a single state and you can make our FSM smaller. Okay. This is the basic idea. Okay. So, let us now show the steps of the minimization, then we shall be illustrating with the help of an example. The first thing to note is that we use something called an implication table or an implication chart. Well, implication chart is basically some kind of a two-dimensional structure which shows the relationship between every pair of states. Let us say S I and S j, whether they are equivalent or not, if they are not equivalent, how they are differing. So, every entry of this two-dimensional structure will capture the information regarding the similarity of every pair of states. This table or chart is called an implication table or an implication chart. Let us see how this table looks like. Now, as I said, this chart I shall show you how it looks like. This chart will have a square for every pair of states, because we want to compare between every pair of states, let us say S I and S j, we want to compare. Okay. And what we put in the squares, that is explained later. So, what we do, the first step is compare each pair of rows in this state table. Pair of rows means actually we are talking about the pair of states. We are comparing every pair of states S I and S j in the implication chart, but that is reflected from the state table. You think of the state table, 2 rows of the state table indicates 2 different states, present states. Okay? That is why we are saying we consider 2 different rows of the state table, and with respect to that we mark the entry in the implication chart. How? So, we compare each pair of rows in the state table. Suppose the rows corresponding to S I and S j. The condition is, if the outputs in the state table associated with states I and j, in short I am saying I and j instead of writing S I and S j, if the outputs corresponding to I and j are different, which means these 2 states cannot be equivalent. In the state table I find that if some input x is coming, the first state is giving an output 0, the second state is giving an output 1. So, they are not equivalent. So, if they are not equivalent, I put a cross in that entry in the implication chart, indicating that the 2 states are not equivalent. Okay? So, if the outputs are equivalent, straight away we can conclude that the states are not equivalent, and we place a cross in the corresponding square I j, the square corresponding to S I and S j I j, to indicate that they are not equivalent. But if we find that the outputs are the same, then we place something called implied pairs in the square I j. What is the meaning of the implied square? Suppose in the state table we find that corresponding to state I for a input, for particular input x, the next state is m, and for the state j, for the same input x, the next state is n. So, what we are saying is that although the outputs are the same, but the next states are different. I is going to m, j is going to n. So, in the implication table, in that square we note down m and n, indicating that they are going to 2 different states m n, but we still do not know whether m and n are equivalent or not. So, we just note them down that they are going to the states m n, we note like this m dash n. We call this as an implied pair. For a pair of states I j and an input x, m n is an implied pair. If the outputs are the same, we put the implied pair in the corresponding square. But if both the outputs and also the next states are the same, which means this m and n are identical, or this I implies I and j implies j, they imply itself, okay, then we can say that definitely these 2 states are equivalent. There we put a tick mark in that square, indicating that these 2 states are definitely equivalent. So, you see, means we are tentatively marking 3 things. First, whether they are not equivalent at all, we put a cross. They are definitely equivalent, we put a tick, but we do not know yet, we note down the implied pairs m n, because we will have to check m n again later to check whether m and n are equivalent or not. If they are equivalent, we will replace them by a tick. If they are not equivalent, we will replace them by a cross. This is how it works. Okay. So, we repeat this for all the squares, go through the table square by square. If a square I j contains the implied pair m n and the square m n in the implied table between m and n, there is a x, which means m and n are known to be not equivalent, then you can press an x in the square. You can mark them as not equivalent. Then after you have done it once, you will have to repeat it. If you find that in the previous step you have added some x, then you will have to repeat the process until no more x's can be added. So, you understand this is an iterative process, this is not a one time process, you will have to repeat this several times, make changes in the implication table until no further changes are possible. And finally, all those squares that does not contain x, you can say that the two states are equivalent. This is how the process works. Now, let us illustrate this with the help of an example, it will be easiest. Let us take the example of a Moore machine, the state table as we have shown on the left hand side. You see there are the 8 states A, B, C, D, E, F, G, H. There is a single input capital X, there is a single output Z. Okay. This table shows that for all input combinations 0 and 1, what will be the next state, and because it is a Moore machine, the output will depend only on the state and not on the inputs. So, the output I am showing only once, or else I could have written D, let us say D comma 0, C comma 0, F comma 0, H comma 0, E comma 1, D comma 1, that is also okay. But because it is a Moore machine, I have shown the output as a separate column. Now, you see the implication chart looks like this as I have shown here. So, I am not showing it as a square matrix, because I need to keep one square cell for every pair. Let us say means along the columns I label as A, B, C, D, E, F, G, and along the rows I label as B, C, D, E, F, G, H. So, this cell corresponds to A and B, A and C, this A D, A E and so on, B C, B D, B, because we do not have to check a cell with itself, A with A or B with B, that is why the number of columns get reduced as we go from left to right. Now, this will be our implication chart. Now, from the table let us see. See, because it is a Moore machine, let us look at it one by one. Between A and B, look at the rows corresponding to A and B, these first two rows. The next states, the output is the same 0 0. Okay. So, the next states are for x equal to 0 D F, for x equal to C H. So, we can write D F C H. Between A and C, look similarly between A and C, you see outputs are different 0 and 1. So, straight away you can write a cross here, they are not equivalent. Then A and D, look at A and look at D, the outputs are same, but the states are D A C E, D A C E, these are the implied pairs. A and E again the outputs are different 0 and 1. So, there will be a cross. A and F again outputs are different, cross. A and G outputs are the same, D B C H, D B C H. Then A and H again outputs are different 0 and 1. So, across. So, like this you will be filling up all the cells. Let us say B and C, look at B and C, outputs are different, cross again. B and D outputs are same. So, F A H E, F A H E. B and E outputs are different, B and F again outputs are different, B and G output is same. So, F B H, well H maps to itself. So, we are not writing H, only F B, the ones that are different those only we will write F B. B and H outputs are different. Similarly, C D, C and D output different, C and E output is the same, E C D A, E C D A. C and F EF dB, EF dB, CNG, CNG outputs are different, CNH, EC DG, EC DG. Similarly, DE output different, DF outputs different, DG, AB, EH, DNH output is different, ENF same output, CF AB, CF AB, ENG different, E and H, C is same, AG, only AG, and F and G output different, and F and H, FC, BG, FC, BG, and finally G and H outputs are different. So, you see this is the first iteration of this implication chart that we have found out. Now, this process will be repeating, like say I am giving an example, let us say the first cell contains DF and CH, we will look at DF, D and F, you see D and F are not equivalent. So, you can say that this will also be not equivalent. Similarly, DA and CE, D and A, this we do not know, DA is itself in fact CE, CE is also something is there not X. So, this you cannot delete. So, wherever you see there is an X, in the next step we will be removing those. So, I am just showing this. So, whatever the first step that we have shown here, I am showing here, and after that wherever there is a mismatch I am crossing them out. For example, this AD is the same self, AD mapped to AD, then C maps to C, I am just cutting them out, C mapping to C. Okay. This is my initial table. Now, after that I will have to check in the next step what are the other things that are getting cancelled out. Like as I said DF, you see D and F there is a cross mark here. So, this will also get cancelled out, I am cutting them out, meaning thereby that I am putting a cross here also. Similarly, you look at this cell AF and EH, AF there is a cross. Okay. So, this also gets cancelled out. So, if there is at least one cross, they will also get cancelled out. Then look at this EF, this also is EF, EF is not cancelled, then BD, this one, right, this one, EF, BD, ENF. Okay. Then BF, B and F is cos, this is getting cancelled out, ABEH, ENH is this AG, AG is already cancelled out. So, in this way you systematically cancel out ones which are not compatible pairs. So, this is the process you go on repeating. Okay. So, you will be repeating this over iterations, this will be after first pass and you continue this pass, wherever there has been some changes made, there may be further changes. Like after another pass, something more are getting cancelled out. So, what we see is that after all these cancellations have been made, you will find that there are still some entries which are not cancelled. Like here we can find these, right. So, here there are 8 states, right, A, B, C, D, E, F, G, H. Now, you see that some states which you are identifying as equivalent C and E. So, we are merging the states C and E. Then for example, this A and D, we are merging the states A and D. Well, this A G also has to be cancelled out, this is a mistake here, this will also be cancelled out. So, there will be 2 equivalent states C and A D, this you can check once, C and A D. So, C E you merge together, A and D you merge together. So, from the initial table you arrive at this final table, which you will see from 8 rows we have come down to 6 rows. Okay. This is the basic idea behind state minimization. Let us take another example, a smaller example of a mealy machine, where there are 6 states and there is one input x. So, the next state and the output are both shown. So, for this the implication chart is shown in a similar way. So, all the state pairs are shown. You see A and B, they are not compatible, because for this output 1 0 outputs are different. So, x. Similarly, A and D are not compatible, 1 0. Then A and F are not compatible, 1 and 0. Similarly, B and C are not compatible, 0 and 1. You see B, D I have put a tick. Why? Because in B and D you see the next state is F, output is 0, the next state is B and D, which is 0, B D are the same pair. So, I can definitely say they are equivalent, I put a tick there. So, similarly, the other things I put, and whichever are the self like BF is the same pair, I am cutting them out, CE I am cutting them out. So, like this is the first step of the implication table. So, we can continue like this. In the next step we will find that some of these are getting cancelled out. For example, B and F, CD for example, you see between C and D there is a cross, between C and D there is a cross. So, CD gets cancelled out. Now, this BF which was there, between B and F you see, between B and F there is CD which is already cancelled out. So, this will also get cancelled out, and again BF has been cancelled out, and BC has also been BC, you see BC is already cancelled. So, this is also cancelled. So, there will be 3 additional crosses that will be added. So, some BD, CE, DF they remain. Okay. So, this is how you continue. So, this is the final state table which shows that BD is equivalent CE and DF. But if you check once more, you see between C and E there is a cross. So, CE also goes out, between D and F there is also a cross. So, DF also goes out. So, only BD remains and no further changes can be made. So, in this table you can conclude that only the pair of states B and D are equivalent, right, no other states are equivalent here. So, this is the final implication chart, and B and D you merge together, and this is your, and means earlier of course, this A and C was also there, AC and BD, these two are there. So, the AC you merge together and B and D you merge together. So, you get the final reduced table. So, like this you can reduce the size of the table. So, in this lecture what we have actually discussed is, given a state table, how we can reduce the size of the state table, which is called state minimization. Now, the process of state minimization is very important before you actually do state assignment and then synthesize in terms of some flip flops that we have seen earlier. But state minimization is an essential step which can drastically reduce the size of the FSM. this specification. So, we will be continuing with our discussion in the next lecture. Thank you.